So far, we have discussed Schrödinger's wave equation, the physical meaning of the wave function, and normalization. The next topic is boundary conditions. Once we say that the wave function describes the state of quantum particle, and once we interpret the absolute square of the wave function as a probability density, then we must ask a very important question. What additional restrictions must the wave function satisfy in order to be physically acceptable? That is exactly what boundary conditions are about. This is an important conceptual point. Schrödinger's equation by itself doesn't automatically tell us which mathematical solutions are physically acceptable. A differential equation can admit many formal solutions, but physics only accepts those that obey the proper boundary conditions. In practice, boundary conditions are often what determine the allowed energies, the allowed spatial forms of the wave function, and whether a solution makes physical sense at all. So up to now, we have focused on what the wave function means and how it is normalized. Starting now, we ask what the wave function is allowed to do at boundaries, at infinity, and at specific points in space. Those requirements will soon become very important when we solve specific quantum mechanical problems. Now let's begin to understand what boundary conditions really mean. Think about a particle or an electron moving through space. As it moves, it may encounter regions with different potential energies. For example, inside a crystal, the periodic arrangement of atoms gives rise to a periodic potential. Or in a simpler model, we may consider a square potential profile like the one illustrated here, where different spatial regions are characterized by different values of the potential energy. The wave function may look quite different in different regions, but it still has to connect properly at the boundaries between them. From a mathematical point of view, this is exactly why boundary conditions are needed. Since the potential energy is different in different regions, the Schrödinger equation generally has different solution forms in those regions. The boundary conditions tell us how those solutions must behave at the interface between adjacent regions so that the overall wave function remains physically acceptable. In reality, the boundary conditions imposed on the wave function and its derivative are usually regarded as physical and mathematical conditions on acceptable solutions of the Schrödinger equation rather than as the central axioms of quantum mechanics. So here we are not deriving them from something even more fundamental within elementary quantum mechanics. Rather, we accept them as necessary physical requirements on acceptable wave functions. So if the energy, capital E, and the potential V of R are finite everywhere, the first boundary condition then states that the wave function must be finite, single-valued, and continuous. Let's look at these one by one. First, the wave function must be finite. It cannot blow up to infinity at an ordinary point in space. If it did, then the associated probability density would become singular there, and the function would no longer represent a physically acceptable state. In other words, for a physically acceptable normalizable wave function, the probability density approaches zero as the distance from the origin goes to infinity. Otherwise, the total probability over all space would not remain finite. Second, the wave function, or equivalently its absolute square, must be single-valued. This is quite easy to understand physically, since the absolute magnitude of the wave function represents the probability density. It would make no sense for the same particle at the same place and the same time to have two different probabilities of being found there. So it would be nonsense to admit two distinct values of the probability of finding the particle in a given place at a given time. Third, the wave function must be continuous. Although the wave function may vary quite differently from region to region because different regions may have different values of potential energies, it must still join continuously at the boundary. For example, if the potential is 0 in one region and non-zero in the neighboring region, the mathematical form of the solution may change, but the wave function itself must still connect continuously across the interface. In 3 dimensions, continuity at a point R0 can be mathematically described by this expression. So continuity means there is no abrupt jump, abrupt change in the wave function at that point. This is the precise mathematical version of the verbal condition stated above. So the key idea of this page is the following. The Schrödinger equation may have different solutions in different potential regions, but boundary conditions tell us how those regional solutions must be stitched together so that the full wave function remains physically meaningful. Now let's go one step further and discuss boundary condition 2. If the energy E and the potential V of R are finite everywhere, then according to the Schrödinger equation, the Laplacian, or the second order derivative of the wave function, must be finite. Otherwise, the Schrödinger equation could not be satisfied unless the potential were infinite, which violates the assumption of finite potential in the first place. And of course, the solutions to the wave equation would be unphysical. So since the energy E and the potential V of R are finite everywhere, Laplacian psi must be finite. This implies that the wave function must remain finite and continuous, and that its first spatial derivative, or equivalently, its gradient, must also behave continuously in ordinary regions. This is a good example to see that differential implies continuous, but not the other way around. In one dimension, this idea is especially easy to see from the time-independent Schrödinger equation. If capital E, the total energy, and the potential V of x, and the wave function psi of x are all finite, then the second derivative cannot contain an infinite or singular term at an ordinary point. Therefore, the first derivative cannot have a finite jump there. Now we ask another question. Could the gradient of the wave function be discontinuous across the surface? Under the present assumption that the total energy is finite and the potential energy is also finite everywhere, the answer is no. However, we may consider situations where the total energy is finite, but the potential energy is allowed to become infinite. If the gradient were discontinuous across some surface, the second derivative would become infinite. The Schrödinger equation could not then be satisfied unless the potential were infinite on the surface or on the interface. So the right physical takeaway is we thus require that the gradient of a wave function be continuous everywhere except where the potential becomes infinite, or more generally, where the potential itself becomes singular. So the key message of this page is the following. The wave function must not only be finite, single-valued, and continuous. In regions where the potential is finite, its first derivative must also join continuously from one region to another. These conditions are what allow us to select the physically meaningful solutions of the Schrödinger equation.